This demonstration is about a GUI that implements the algorithm in my paper that to recover the right rotary center during the deblurring of a degraded image. So first, we should synthesize a deblurred image, a degraded image by rotary motion simulation. And the first procedure is to load an image, which is a clear version. Okay, and we click it. And now this clear picture has shown here. And the red triangle symbolizes the center of this image, but actually it does not necessarily uh, the center of rotary motion. And then we give some input rotary motion parameters to do the degradation. And first is the blur angle. Blur angle is defined as the angle spent by the camera during the camera exposure time. So we can give a 15 degree. And then we add some Gaussian noise, which has a 30 dB SNR. And here is the parameters about the location of the rotary motion. In the upper row are two boxes, and we can give 3 and 5. And if we give 3 and 5, this means that the real center of the rotary motion located from the right triangle 3 uh, pixels horizontally and 5 pixels vertically. And then we assign a radius. A radius is about the actual area that is used to degraded by the rotary motion. And here we can give 120. Then we synthesize the blurred version. It takes a little time. Okay, now there shows a green box. The green box uh, actually gives the actual area that is undergo the rotary motion degradation. And the rotary motion degradation is just subject to these parameters. And then we, based on these known parameters, we can give a deblurred version. And the deblurred algorithm is used in my paper as well. Okay, and here we got the deblurred version. And then we can test our algorithm of how well it can recover the right rotary motion center. And first we should import the blurred uh, image. Okay, click this button, and this picture is actually imported from here, and they are the same. And we can give some rough parameters to guide the calibration. So as here we should suppose to not know these parameters, and actually we should make a compression between the real rotary center and the one recovered from the program. And these two bugs finally gave the recovered version. And but first we should give a rough estimation. So we can give randomly, but not too exaggerate. So we give 4 and 7. Okay. And we should also input some other parameters. And the first one is the voting circle index. Voting circle uh, is a series of concentric circles around every center candidate. And you know there are some circles cannot give reliable results, so we should give we should assign what kind of circle that can give reliable results. So we can here input 30 to 120. And these two parameters can always be transported for any other cases. And this can be seen as a recommended version. And you don't have to modify it very frequently. And so is the frequency range. And frequency range is that we note that we implement a certain algorithm in the spectrum which is in Fourier domain. So we can input 10 to 60, and then we show the certain box, the little green box, and the right rotary center is here, but we don't know which pixel is that. And then we start the calibration program, you know, and here, while the MATLAB is doing the calculation, we can see here is that is the algorithm is very computationally expensive, and actually it should evaluate for every center candidate of how well it fits the real rotary center. And in this case, it runs for 25 times, and the result is a voting map. And then we should, of course, to know the white box is symbolized the recovered one, and actually the left upper left one is symbolized the rough center, and based on the displacement we can from here we can recover the right one, that is which is 3 and 5. Now we compare it to the right parameters. Yeah, they are the same. So it proved that the algorithm to calibrate the right rotary center is justified. And finally, we give the degraded image based on the recovered parameters. Okay, and actually they are nearly the same. Okay, that's it.